Yes, we can hear you.
Oh, excellent. Okay. We have about 5 minutes left before the lecture starts. I just have to try to send on my iPad to actually show you the slides. Until then, okay, 1 second. Turns out that my security precautions to only let in certain email addresses just backfired on me because my iPad is signed in with the other address. And that is kind of the problem now, but we still have 5 minutes to figure that out. I just hope that I'm allowed to join twice the same meeting with 2 different accounts.
Hello. Mic check.
Yes, your microphone is working.
Nice. Nice M50Xs, by the way.
How many? We have 50 participants right now. Oh, that looks very good. Actually, no, I don't want to have 2 videos. And only 1 audio would be better too. Okay. Let me just check this image in focus. Where do I check this? All right. Screen share. So I hope you can all see the screen of my iPad. It's supposed to be the lecture notes. I've taught many classes. I mean, 1 class online, 1.5, no, half a class online too. But this is the first one on Zoom, so I'm just trying to understand all the, just make sure that everything is working the way I want. Okay, let's test the raise your hand functionality. Can everybody just raise their hand? If you go onto yes, okay, I see many raised hands. That's excellent. I have a button to mute you all. I do want you to be able to unmute yourself. And yeah, I can see the chat. I'm going to ignore the chat for most of the time unless there's a question. So I guess I can just start by telling you something about Zoom. So the way that I intend to use it is that if you have a question, please do not unmute yourself directly, but just raise your hand. And then I see that, hopefully. And then you can ask, then you can unmute yourself or chat. I don't know if you prefer to talk or just write. And I'm also going to take breaks, not breaks, but I'm going to pause at some certain points for questions specifically because I feel like that's the point where questions make the most sense. So don't. So bear with me for a few minutes if I maybe sometimes do not. I'll answer a question right away, but I have a feeling that sometimes a question right after the definition, for example, is going to be not so good. It's better to see an example first, and then many questions will already be clear. Okay, so I guess we should start. It's 10 past. As you hopefully know, the lectures always start 10 after the hour. And first of all, I would like to encourage you to turn on your webcams whenever you can. I see there's 66 participants and only 2 students have the webcams on. And I mean, I already feel like I'm talking to a computer, and that is actually the truth. But if you could turn on your webcams, it'd be more like an actual lecture in a classroom than just me talking to a computer. Maybe actually. Oh, I see more. Sorry, that was my mistake. I see many of you have the webcams on. That's great. For some reason, Zoom doesn't order the webcams first. So I mean, I kind of want to see myself just to check that the video is working. And I see my screen mostly. I guess that's fine. Okay. All right. So welcome to the class. This is Linear Algebra 2. MAT224, and this is a coordinated course. Your course instructor, we have a coordinator who's doing all the politics of the course, who's designing mostly the assignments and making sure that the course is working. And my primary job is to deliver the lecture for your section. As I wrote here, just a little bit about myself. I'm a PhD student in the math department in Toronto, and I work in differential geometry. And geometry is actually a lot of linear algebra. So linear algebra is mostly the basic of differential geometry. If you have questions about the course, depends on the kind of question. If it's a question about the content, then you can use Piazza. That's a forum for asking math questions, and then other students and instructors can all discuss the question. If you have a question about the lectures or course related otherwise, this is my email. I wrote it in this forum so that eventually, if this email can't be like copied easily, but if you see this, at one dot will be symbols. I will also host office hours specifically for this section, and this will be Wednesdays just before this lecture, so at 2 p.m. EST. And the office hours will not be recorded. This lecture is recorded, and maybe I should have started with this. So I'll be recording this, and I'm going to make this available on YouTube for 1 week. It's not going to be public. It's going to be listed on YouTube, but you can only access it with a link, and then I'm going to delete it afterwards. So I don't know if that's a concern for you. It might be possible that in this YouTube video you'll see your tiny face in the tiny video. Just to let you know. Right, I should just follow the slides, by the way. That would make a lot of sense. So details about the course on that there are assignments, for example, how much the assignments are worth. All these informations can be found in the syllabus. So the syllabus is on Quercus. I can just show you. You go to the modules, and then you see syllabus on the top left, and this is 10 pages. A lot of information that I will not all go through today. But basically, if you're wondering about the structure of the course, you can look this up. You've successfully come to the Zoom meeting, so I assume that this is working for you. I'm going to send an announcement later that to everyone who has trouble with the Zoom meeting, we have to figure this out. We can have a textbook, which is by Damiano and Little. And the content will is building on what you learned in MAT223. This is a prerequisite. The main difference is that this is going to be more abstract. So this is going to be not just in R2 and R3, but we need to talk about Rn, and all the concepts that you learned before will be more abstract. And this is very powerful because if you're able to talk about something abstractly, it means that you're not talking about the example, but you're actually talking about the concept. So we're going to teach concepts in this course. And also proofreading is a very important aspect, meaning that you should be able, and at the end of this course, to deliver a proof, which is to say that you can coherently state mathematical steps and one follows from the other. So that's a very important step in maturity in mathematics. Okay, at the end of the syllabus, this is probably the most important part of the syllabus. There's a weekly class schedule. So you will see week for week what it is that we're going to cover. Let me just go down there. So for example, this is week 1. So after this introduction and a bit of recap of basic math, we're going to talk about vector spaces and subspaces. And I'm going to put up lecture notes for every week. And they'll be exactly covering this part. So we're going to follow this schedule. Right, the lecture will be recorded and it's going to be only available for 1 week because we want to help you not to binge watch this as a series at the end of the semester, but to help you stay up to date and watch this within 1 week of the lecture taking place. Right, about the lectures. So I'm going to be explaining a lot, but I also want you to participate in discussions. That means after definitions and examples and theorems, I'll give you some time to think about that. I'm going to pose questions to you, and I don't think we're not going to try breakout groups today, maybe sometime later. But after you've had like maybe 2 or 3 minutes to think about a question, you're welcome to chat amongst each other. One thing I would like to ask you is to not spoil the solution, because that's going to be, I mean, it's just nice if everyone has the same time to think about the problem. And then we're going to carry together. And as you see, I have a pen. I can write on here. We're going to annotate this, and there's going to be blank space in between. So it's a little bit of fill in the blanks in between the theorems. Right, but I want you to participate because I think that's more valuable than just listening to me for 1 hour straight. Is anything I forgot? Oh, right. So as I said, many of the theorem's definitions will not be numbered because they just doesn't matter what number they are. But if they appear in the book, in the textbook, and they have a certain number there, then I'll always try to give it the same number so that you don't have 2 different names for the same theorem. I think that would be just confusing. So the most important theorems that will also appear in the book, they will have the same number, so they can always go back. In fact, the weekly schedule always gives you the sections corresponding in the book, and then you can just go there and see the same statement again. Yeah, I said that these lecture notes will be available. There will be plenty of mistakes because I'm writing them from scratch this semester. I would like to thank Professor Sean Upal, our coordinator, and a friend of mine, Jeffrey Im, for providing me their slides from the previous course that they taught. They had the same course, but they taught it previously. So that helped me a lot to prepare these lecture notes. But because I'm writing them from scratch, there'll be plenty of mistakes, and it would be great if you could point them out. Just send me an email or let me know if something is funny here going on. Well, I already lost track of the bullet points. Right, we use the same Zoom for office hours and lectures. I think that's just easier. Please don't share those publicly. Yeah, I think you already unmuted yourself. That's great. You can raise your hand. And yeah, if I pose a question and I'm actually expecting answers from the chat, it would be great if you can, if you don't spoil the answer first of all, and then only message course relevant messages, because if there's just like a flow of messages coming in that's not relevant, then I'm going to be just looking for all those important messages in between. Well, that's it for the setup and how it's going to work. Any questions at this point? Okay. I don't know. Is there a thumbs up function in Zoom? I think there is something. Oh no, I lost the chat. No, there it is. Okay. Can someone just give me a thumbs up? Is that possible? Can you figure that out? think I was able to do that before in meetings. No, it doesn't seem to be possible right now. Oh, right, I can ask polls. Okay. Oh, but this doesn't really, this is opening a weird window. Let's not do this right now. Okay, so I'll just hope that you will give me feedback if I go too fast or too slow. Because if I don't get feedback, it's always really hard to tell if I should speed up or slow down. I usually tend to go too fast in the end. I have observed that for myself, so I'll try to counter work with that. If there's no questions, oh, the chat. I think I didn't check the chat. Okay, so if you have questions, please put up your hand. Actually, there's still hands raised. Can I lower them somehow? Yeah, I think so. Okay, lower all the hands. Okay, so whenever you have a question, just raise your hand and I think I'll see that. Oh, someone just said that you can lower your hands yourself. That's fine. I'll think it's just a quick click with the mouse here. It's fine. Okay, so 10 minutes in and we're already at the math part. That's going pretty good so far. So the introduction is going to be a few slides just about some basic math that I think you all know. But I thought I'm going to start this with an introduction so that we also have the same notation so that you get used to the notation that I'm using in this lecture. So I want to talk about a set for a little while, just like this slide. So it's a set. I'm just denoting a collection of objects, and the notation is often with squirrely brackets. Sorry, curly braces. And the set could be, for example, the integers, the real numbers. So anything that's just resembles a basket of, say, apples. That would be something like a set. And the integers, I guess, the real numbers, we can talk about non-negative real numbers, so anything 0, 1, and up. And when we want to say that one set includes the other, we use this notation, but be aware that this might be actually a non-proper inclusion. So it could be the case that A and B are the same, then we would still use the symbol. And we call this a subset. So many subsets are actually declared by conditions. And this is what I mean here. You can prune a set by a specified condition. So if you write this, then you select all the elements in a set, and then you sort out the ones that do not satisfy this condition. In this case, if you want to have the even integers, then you would say, okay, I start with all integers, and then I prune out the ones that are not odd, they're not even. So only the ones that are even are remaining, and same with the odd integers. This is just standard notation. Just to everyone to be on the same page, I thought I'm going to include this. And lastly, on this slide, if there is a set that is strictly included, so this means that there's at least one element in B that's on an A. I should start drawing pictures, I guess. So if this is a set, and this is a subset, but there's one element, namely this one, which is not in A, then we say that this is proper. Whereas if we have set and a subset, sorry, this was supposed to be this color. So this is A and this is B, and every single point is in both of them, then we say that this is not proper. A is in B, and here also A is in B, but it's not equal. Okay, any questions? All right, next up, I want to remind you of functions, specifically notation that we're using here. So if we have a function between two sets, it's just an assignment that picks out elements from one of the sets and assigns it to an element in the other set. So this means you could, I think the standard picture to draw here is you have a function from A to B. You're just going to draw these sets. And then for every element in A, you draw an arrow that ends up somewhere in B. So this would be a function. Notice that you can't have two arrows starting at the same point and going to different ones, because it has to be an assignment. So you can't assign an element in A to two different elements in B. I mean, that just then, I mean, what is f of x in this case? It doesn't make sense. So as an example, I listed here the function from z to z, so between the integers. And this notation, so be aware that this notation is very important. If the arrow has this little vertical bar at the beginning, this means I'm talking about the elements. So this is element level. Oh, this pen is too big. This is elements, and this is the sets. So if this just means it's going from z to z, and if it's assigning x to 2x plus 1, then I use this arrow, and this is equivalent. This second line is equivalent with writing g of x is equal to 2x plus 1. Right, there's a few definitions, just a few notational things, just naming conventions that I want to go through. So the domain is always the thing, as always the set where it takes values in. Sorry, other way around. The domain is the one that the values come from that we can plug in. So this means f of a makes sense. So f of if a is in the set A, if it's the domain, then f of a makes sense. And the codomain, or we can also call it the target, is the set where it takes values in. So this is where it projects in. So it's always going from domain to codomain. And then just a wording thing is we say that f of a, if you have an element A where it is valid to apply the function to, then we say that f of a is the image of x under f. So it means that f is the thing. I should delete this arrow, which isn't allowed. So if we have an element A in here, let's say this one, and then we send it here, then we can just, I always view this as arrows shooting from one set to the other, and this is just the arrow f. So lastly, two last lines, there's the set of all functions between two sets. So if you specify A and B, I mean, if you change one of these arrows, if you say, for example, this one doesn't go down there anymore, but it goes also up here, then we change the function. So we have different functions for two fixed sets. And the set of all these functions is denoted by f of a comma b with this calligraphic f. And lastly, whenever we have a set, we can always define a function that goes from the set. Let this be A, and these are the elements. Then we can always send it back to itself, every element. So I guess that's the best picture I can draw for this. And this is always called the identity function, ID. Identity function for the set A. I'm kind of realizing that I'm mostly writing things myself and not so much using the type stuff. Or maybe I'll adjust that in the future lectures. Any questions so far? Oh, I see there's a question. Why is the image of x on the line like image of x under f? I don't think I understand the question. No, the codomains are not the range. We're going to talk about this in the next slide, actually. So the range in this case, I mean, I guess I can just say it here. The codomain is all of B, but the range is only the things that get hit. So this is the range of F, because it's like every point where an arrow lands in. So no point in here is without an arrow. I guess I could have included that. That's a good question. Thank you. Oliver, you have a hand up. Can you unmute yourself? Oh, I'm not allowed.
Can you hear me?
Yes, I can hear you now.
So the F, the fancy F bracket A to B notifies that a X value goes to two X values go to a Y value, to one Y value. Is that what it's
Oh,
stating?
this one.
Yeah.
No. So what this means, it's just the set of all possible functions. So remember that up here I said that Z. I mean, if we have Z, so if A is equal to Z and B is equal to Z, then what are the functions? So I mean, there could be a blue arrow, a blue function. There could, I mean, we just call this F, and this G, and this H, and we said that G of X is equal to 2x plus 1. But that's not the only function we can define from Z to Z. There's many more. So for example, we can say that G of X is equal to 3x, or we can say that, sorry, not G. Now there's a different function. So there's a plethora of functions between any two sets. So if you fix the sets, then there's many functions. There's not just one or two. And to describe the set, as I said, it's a collection, it's just a basket of apples or something. To describe this set of all possible functions, I'd use this notation. So I would say that if G is such a function, then I would say that G is inside F AB.
I understand now. Thank you.
Okay. All right, other questions? I'm realizing that we should probably speed up a little bit. I want to at least come to the definition of vector spaces at the end of today, and we have half an hour left. Okay, so now we come exactly to the point that I was going to make about the range. So there's three important properties that a function can have. It could be injective, surjective, or both, which is bijective. Now let's just focus on injective for now. Injective means that any arrow at any point in the target is hit by by only one, at most one arrow. So that, in other words, what I wrote here is no two distinct elements have the same value. So if we draw this, maybe we should have left some space in there. I'll figure this out next time. Okay, so here, say that this is the function. This is F. This is not injective because we see that there's two arrows that come together to this point. So this is two arrows hit this point. Whereas if we, I mean, let's visualize the 2x plus 1 picture. So if this is 0 and this is 1 and so on, then 0 would go to 0. But 1 would go to 3. Sorry. So in here, it is true that there's only one arrow coming in, at most one arrow to every point, and then we call it injective. Surjective means that every point in the target is actually hit by some arrow. It doesn't matter if it's more than 1 or if it's more than 20, but at least one arrow hits it. And this is exactly, so let me draw a picture for this. So if this is the setup, and let's say that this is left out. So this is no arrow goes here, and therefore not surjective. Whereas if every element had an arrow coming in, then it would be surjective. And bijective just means it's both injective and surjective. Okay, so now a quick question. Which of these properties, injective, surjective, and bijective, apply to the function g of x equals 2x plus 1? I'll give you 1 minute to think about this, and then maybe one of you can tell me what they came up with. All right, can someone raise their hand? Oh, I see. Raghu, do you have an answer? I just asked someone to unmute. I don't know who it was.
Okay. No, before I didn't raise my hand because of the answer. It was regarding the injective definition that you had above. I was just confirming, shouldn't it be the other way around? A does not equal to B implies f of A does not equal to f of B. Because I believe this one, it's like f of A equals f of B should imply that A equals B.
No, it doesn't. Because in this case, say this is A and this is B, then this could be the common image under F. And then it could be the case that that f of A is equal to f of B. But then, so if we have two different points here, I think this is correct. Does that explain the question, or?
I guess kind of, because I tried it with a few examples and I tried to prove it, and I find that the other way works as the correct definition.
Okay, let me think about this when I'm not
okay
on the spot because yeah, I'll just put a question mark. Maybe I've gotten this wrong. That would be really embarrassing, but maybe I've gotten this wrong, and then I'll check this later. I'll update this if it's wrong. Or can someone else confirm that they? Oh, okay. Yeah, I think. Sorry. In this case, yeah. So this might be wrong. The first line is correct, though, I believe. So if, as I said, if you have two distinct elements, then they don't have the same target. So if you have A and B, and A is not equal to B, then f of A is not equal to f of B. So the contrapositive of this exactly is that if we have f of A is equal to f of B, then this implies that A equals B. Yeah, now it makes sense to me. Thank you. I was not thinking about this straight when I was writing this. So the first line is correct. I'll update the second line. So please excuse this failure, this mistake. Yeah, but I hope the concept is clear that if at most one arrow hits, so if there's no arrow, no two arrows coming here, then it is injective, and if there's more than one arrow coming, then it's not injective. Okay, can someone tell me about this function? What do you think about this function? Is this injective, surjective, or bijective? Jeffrey, can you tell us something?
Yes. So I said it was bijective. It's a linear function, so it makes sense that you can't have an output same two different inputs because it's a linear function. So it's injective.
It is injective. That is true. It is not linear. That's why I was worried to do anything about this. We're gonna say later what linear means in a later lecture.
As in the power of x is only 1 at most.
Yes, that is true. So it is a line. If it was like between R and R, that is true. Yes.
Right. So you can't get the same output for two different inputs. So it has to be injective. And
exactly.
And for the surjective part, any kind of output you get, you generate it from some kind of an input. That's how you solve like a linear equation.
Well, notice that I just wrote here, this is z to z. So this means that we don't have any real number available for x. And this is exactly the kind of trick behind this question. Well, I just wanted to make you aware of the domain, the codomain. So this means that the even numbers, so observe that this is always odd.
Oh.
And this is explaining the reason, because this is always an integer. So as I was drawing here, so we skip. Sorry, no. I was drawing this wrong the last time. So this goes to 1, and then 1 goes to 3, but 2 is left out, and 3 is going to 5, 4 is going to 7, and so on. But you can see that there's always a number being left out. So in this case, it is injective. That's correct. It is not surjective. But I was also asking here, if not surjective, how can you change the definition to make it bijective? So can someone maybe say something about that? No, there's already hands raised, so I don't know how to. Okay, I think Adrian just raised a hand.
Yeah, so I think if you would just change it from the reals to the reals instead of the integers, then you could actually make it bijective.
Yes, that is true. So we could, for example, make some space here. So we could change domain and codomain So we would have that G is going from R to R. Actually, I was not thinking about this, because what I was thinking someone would say, we could also change this from Z to only the odd integers. The odd integers. I'm not sure right now though if -1. Yeah, it should be fine. So so if this is the so if this is X in Z, it's just that X is odd, then we would exactly eliminate all these even numbers in here, and then we would have only the odd ones remaining, and then it would be actually surjective. So the upshot of this is, I guess, that the domain and codomain are actually very important for maps to consider. Any other questions? Okay, I have to keep track that I actually lower all the hands before I move on. To lower all the hands before I ask if someone has a question, because then I don't know if this is an old hand being raised. Oh, I see that someone actually answered questions in the chat. That's great. If you can answer your other students' questions, that's great if there's a discussion going on. Okay, so actually now I'm worried that we're not going to get to vector spaces in the last 14 minutes. Okay, very quickly, composition. This is not really anything too difficult. It just means that, so if you have a function that goes from A to B, as I wrote here, and then a function that goes from B to C, what you can simply do is whatever the one function has as its value, you plug into the new function, so the another function. So it is just literally a concatenation of functions. So if you have A and the function from A to B, and then a function from B to C, then say A is in here, the little a, then of course we're going to have f of A in B, and now we're allowed to apply G because B is the domain, and it is allowed to apply function to everything in the domain. So the important bit is that the B here and the B here, they're the same. Okay, and then of course what we get is G applied to the image of A under F, so it's G of F of A, and that's already it. And then because we don't want to write just write so many parentheses, there's if you forget about this stuff in the middle, so let me just literally put a black box around this. So treat this, or let us maybe just say that this is now a black box, literally. Then all you see is A going in and G of F of A coming out. So it means that you basically just want to like hide the thing in the middle. And this is happening by you can just write an arrow from A to C. And then this function, which is the concatenation of these two, we just write as G compose F. So this is exactly what I wrote here in this this yellow box. So that if you have two functions and you concatenate them, you just use this little circle as a symbol. Any questions? And of course, this is a new function now. So if you have two functions before, then you can make a new function out of these two. Oh, I'm going to write these elements of symbol in all kinds of directions. I might even write this sometime, so be aware. Okay, if there's no question, then let me go to the next page. So now the composition of functions, the concatenation, is very important because this is how we define an inverse. And well, if you have a function, then an inverse is kind of, think about it as another function that undoes what the previous function did. So if you Yeah, I don't know where to start in this slide because there's so much text. I should probably write less text for the next slides. So if you have a function going from A to B and another function going the opposite way, so going from B to A, you could also write this just backwards, just going this way, then if their composition of either way, so this is to say that A composed with F, so H composed with F, and F composed with H is not doing anything to the elements. So if they exactly cancel each other out, then we say that they're inverses. But notice that if you write this, then if you write H composed F, then this will take elements in A because F goes, let me just make this a little bigger here. So F goes to the right and H goes to the left. Then if you apply this, you can only apply this to A because F is the first function, so you can't apply this to a little b because that wouldn't be the domain, it would be the codomain. So this would be H, FF, FA. And what we want is we want this to be A. But this is equivalent to saying that H composed F is equal to the identity function on A. And then same for F composed with H. Now this is only applicable to B's because again, the B is the domain of H. And so we go this way around the circle. Maybe I could draw this. So this is the one. And then if we go this way is the other. And they both have to be equal to the identity of the respective sets. So one can only be the identity in the one set and the other one in the other set. So this has to be, this is equal to F of H of B. And we want this to be equal to B for all B and B. But this is also just shorthand notation is equal, is to say that F composed H is ID sub B. So for this function that we saw before, g of x equals 2x plus 1, we saw that it multiplies it by 2 and then adds 1 to it. So we saw that, what was it here? Let me go back here. So now the idea would be if we go back, I mean, how do you undo adding 1? Well, you subtract 1. How do you undo multiplying by 2? You divide by 2. So you want to find a function that is not going that is going backwards. So I should be careful now because it doesn't make sense. So now you see the problem with not being surjective. So if I wrote a function here going from z to z, say h, and h of y is equal to y minus 1 over 2, who can see the problem? Yeah, Raghu.
Yeah, so like since like it wasn't surjective, that means like you would have an arrow going from to z, and it wouldn't be pointing to anything in the domain because originally it didn't have a mapping to it.
Yes, exactly, that's true. And the way we can see this here, I was hoping for that other answer, but I'm aware that it's very mean to ask a question and only accept one answer. So that is completely right. So this is not an integer. And it's equivalent to what Raghu just said, that if you divide an integer by 2, if it's even, well, then we're lucky. But if it's odd, then we're going to have like 1.5 or something. We are going to have 0.5 away from an integer. So, and this is the reason why this inverse doesn't exist from z to z. So now, yeah, sorry, I went a bit. I wanted just to go up to like show you this. But now, actually, let me move this down and shrink this a little bit. This is something I couldn't do on the blackboard, and this is actually pretty cool. So now the theorem that I want to end this introduction with is that a function is invertible. So this undoing thing exists if and only if the function is bijective. And this is very important. So as we saw, just let it sink in for a bit, because this is the interesting thing here about this theorem is it doesn't give you an inverse. It just says it exists. So it doesn't. It is not a concrete theorem where it says like, well, this is the inverse. There's another question. I'm afraid to pronounce the name. Zijin. If you can unmute yourself, please ask.
Yeah, you can just call me Claire. My question is that is identity A equals to identity B?
Oh, so you mean if?
Yeah.
If this is equal, if this is true?
Yeah.
No, the answer is no, because these maps have different domains. And also different codomains. So while IDA is going from A back to itself, and IDB is going from B to itself. Or you could also write it's going from A to A, and IDB is going from B to B. So for two maps to be equal, only really makes sense if they have the same domain and codomain. So if we say maybe there's some set X and set Y, and there's functions G1 and G2, then we can say G1 is equal to G2 if G1 of X equals to G2 of X for all X in X. So if they agree on every point in the domain, then they're equal as functions. But IDA and IDB don't even have the same domain and codomain. All right, so one thing I want to say about this relating to the function g of x equals 2x plus 1, this is a perfect example to see how this theorem can help you, because, well, intuitively, if you, I'm not going to bother writing those numbers here, but just the option was there's things being left out. So those were the even numbers. So because this is not surjective, as a function from z to z, the inverse can exist. And this is good because okay, let me first say that z going on to only the odd integers is surjective. Well, it actually is bijective. So now the inverse exists. And well, it's not hard to guess now what the inverse might be, because I said that, I mean, g of x doubles an integer and adds one. Well, then h of y, we can just say this is y minus 1 over 2. And then we can actually check by hand that h of g of x is equal to 2x plus 1. This is the value of g of x, and then we plug this into h. So we subtract 1, and then we divide by 2. So then we can simplify this to 2x plus 1 minus 1. They cancel conveniently. And then we get x. So you'd have to just do the same for the opposite, meaning that g of h of y is equal to y. So this is the question mark. So you might ask now, and this is the what I want to say before I stop the lecture. This function h exists, but the question is it well defined if we go from z to z? So even though this function, you can always write down this function, it doesn't make sense to write this down as a function from z to z. So this is exactly why this isn't surjective. So this is exactly why the theorem works in this case. So let me just maybe make this the last remark in this corner here. So h of y equals y minus 1 over 2 is not defined as a function going from z to z because y minus 1 over 2 is not an integer if y is even. And therefore, it can't be an inverse for g going from z to z. So even though you can write down the term of h, it doesn't make sense as an inverse. It's not able to assign a value to every element in z. And that's why, even though you can write down the term, we still say there is no inverse. This is a rather subtle point, but I think it's important to point this out. And this is exactly why the theorem applies here. Okay, we got exactly to the last page of the introduction. This is great because then we can just start with vector spaces tomorrow, actually. And then we're actually going to talk about what these slides promised about vector spaces and subspaces. Are there any questions about what we did? Do I have to say anything at the end? Well, I'll put this up on YouTube for 1 week. I'll send you a link over the announcements in Quarkus. I'll fix this mistake here. So this is a mistake that I made, and I'll correct it for the next lecture, and then I'll remind you. But other than that, thank you for your attention, and I'll see you tomorrow. I'll stick around for 5 minutes or so if there's any questions. Oh, there's raised hands. Yes. Okay. I just go one by one. Daniel.
Hi. Do we have any homework for the first, I guess, lecture, or would it just be to review the notes and get ready for next class?
So I'm not going to assign you homework for the lectures. I mean, I have those discussions, but I want to do them in person. So don't expect any homework from the lecture. There's going to be assignments, and so it's going to be homework from coming from Sean, our coordinator, Professor Upal. So that's going to be homework to be handed in. Yeah, you're welcome to review the lecture. It's going to be on YouTube, so you can rewatch it in the next week. You can also read the slides. You can read the book sections if you want, if you think, if you want to see another version. So I'm going to cover basically everything that is relevant, and that means that I'll cover most of the things that are in the book in some way or another. I might rephrase them a different way. So there's no necessity to, I mean, yeah, I think it will be good to read the book, but you can expect that everything that you learn here will also be in the book, so you can just compare it.
All right. Thank you very much.
You're welcome. Okay, Mallory, please unmute yourself.
Hi, I just had a quick question from the last page of the notes that we got to today. When
Yes.
you redefined the codomain for G so that it would be bijective, what was the symbol? Was it the rationals?
Oh, sorry. Honest, I don't think even this is an official notation. I was just making this up. So this is the odd integers.
Oh, okay.
So I technically defined it in the second slide or so. Yeah, I defined it here. I don't think this is accepted notation, but just be bold and make your notation. So just, if it's convenient, just come up with it and go with it.
Okay, perfect. That makes a lot of sense. Thank you so much.
Sure, you're welcome. And I think Jeffrey is the last raised hand.
Hello. Yeah, so as for the mistake line in the injective definition,
Yeah.
a decent fix for that would just be to convert the not equal sign into equal signs, right? Two of them.
You mean the second line?
Yeah, so just an easy fix would be to change not equals to equals in both cases, right?
Yeah, let me think about this. So what we want is that if you have so what can't happen is this, right? This can't happen. So this means if we have something in here, if we have one single point in here, say this is f of A and f of B, and if they're the same point, then this has to imply that they are also the same. So yes, I definitely agree with you. That's a very good fix.
Okay.
So, I mean, I made these lecture slides over the past weekend, and I read through them 5 times, and just like edit here and stuff here and there. And I did not imagine that something like this would happen. But I'm glad that you caught one of you caught the mistake. Okay. Yeah, this is definitely correct.
That makes sense. Thanks.
All right. Other questions? Yes, I will let you know what the link to the YouTube is, of course. So you don't have to like go look for it. That would be ridiculous for me to ask. All right. Then I'll see you tomorrow. I think is it 1 p.m. tomorrow? I lost track. 1 second. Yeah, it's 1 p.m. Toronto time. So I'll see you tomorrow, and I'll end the lecture now.